Now, whenever we interpolation operation should have certain desirable properties. Firstly, the interpolation function that you use for interpolating the discrete values, that should have a finite region of support. That means, interpolation should be done based on the local information, it should not be based on the global information, or it should not take into consideration all the sample values of that particular digitized signal. The second desirable property is the interpolation should be very smooth. That is, the interpolation should not introduce any discontinuity in the signal. And the third operation is the interpolation should be shift invariant. So, if the signal is shifted or given some translation, then also the same interpolation function should be available, should be done. And the B-spline function is one such function which satisfies all these three desired properties. Now, let us see what is this B-spline function. B-spline function is a piecewise polynomial function that can be used to provide local approximation of curves using very small number of parameters. And because it is useful for local approximation of curves, so it can be very useful for smoothening operation of some discrete curves. It is also very useful for interpolation of a function from discrete number of samples. So, let us see what is this B-spline function. A B-spline function is usually represented by, say, x t is equal to sum of p I into b I k t, where you take the summation from I equal to 0 to n, where 0 to n, that is n plus 1 is the number of samples which are to be approximated. Now, these points p I, they are called the control points, and b I k is the normalized B-spline of order k. So, b I k, this is the normalized B-spline of order k, and p I are known as the control points. So, these control points actually decide that how the B-spline functions should be guided to give you a smooth curve. Now, this normalized B-spline, that is b I k, can be recursively defined as b I 1 is equal to 1 whenever t I is less than or equal to t less than 1. So, this is b I 1 of t, it is equal to 1 whenever t I is less than or equal to t and which is less than 1, and b I 1 t is equal to 0 whenever value of t takes other values. So, this is equal to 1 for all values of t lying between t I and 1, t I is inclusive, and b I 1 t is equal to 0 for any other value of t. And then we can find out b I of and k of t using the relation. So, b I k t is equal to t minus t I into b I k minus 1 t upon t I plus k minus 1 minus t I plus t I plus k minus 1 into b I plus 1 k minus 1 t upon t I plus k minus t I plus 1. So, once we have b I 1 for different values of t, then from this b I 1 we can recursively compute the values of b I k using this relation. Now, find that once we have this relation of b I k t, you can easily verify that once I have b 0 k t, then b I k t is nothing but translates of b 0 k t. So, this b I k t can be written as this is nothing but b 0 k t minus I. So, this can be easily verified from the way this B-spline function is defined. Now, this B-spline function for various values of I and k can be obtained like this. You can easily get that b 0 1 t will be equal to 1 whenever 0 less than or equal to t less than 1, because earlier we have said that b I 1 t is equal to 1 whenever t I is less than or equal to t, which is less than 1, and it is 0 otherwise. So, just by extending this, I can just write that b 0 1 t will be equal to 1 whenever t lies between 0 and 1, 0 inclusive, and it will be equal to 0 otherwise. So, you find that b 0 1 t is constant in the region 0 to 1. Similarly, we can find out b 0 2 t will be equal to t for 0 less than or equal to t less than 1. It will be equal to 2 minus t for 1 less than or equal to t less than 2, and it will be equal to 0 otherwise. Similarly, you can find that b 0 3 t can be written as t square by 2 for 0 less than or equal to t less than 1. This will be equal to minus t square plus 3 t minus 1.5 for 1 less than or equal to t less than 2. It will be 3 minus t square upon 2 for 2 less than or equal to t less than 3, and it will be 0 otherwise. Similarly, we can also find out b 0 4 t will be equal to t cube by 6 for 0 less than or equal to t less than 1. It will be equal to minus 3 t cube plus 12 t square minus 12 t plus 4 by 6 for 1 less than or equal to t less than 2. It will be equal to 3 t cube minus 24 t square plus 60 t minus 44 divided by 6 for 2 less than or equal to t less than 3, this will be equal to 4 minus t cube by 6 for 3 less than or equal to t less than 4, and it will be 0 otherwise. So, we can obtain all these values from the definition of the definition of the B-spline function that we have defined earlier. Now, whenever I write this B I k, this k is called the order of the Bezier order of the B-spline function. Now, after giving these equations, let us try to see that what is the nature of these Bezier of these B-spline functions. So, you find that B I 1 t, because it will be equal to 1 for I equal to 1 to 2, between I equal to 1 to 2, this B I 1 t will be equal to constant and it will be equal to 1. So, this first figure in this particular case tells you that what is the nature of this B I 1. The second figure shows what is the nature of this B-spline function if it is B I 2 t, and it shows that it is a linear function. So, B I 2 t will lie between, will have a support from I to I plus 2, and the points which will be supported by this B I 2 t are I plus 1 and I plus 2. Similarly, a quadratic function which is B I 3 t is given by this figure, and a cubic function which is B I 4 t is given by this fourth figure. And here you find that the region of support for this cubic function is 5 points, the region of support for quadratic function is 4 points, the region of support for the linear B-spline is 3 points, whereas the region of support for for the B-spline of order 1 is only 2 points. So, in all the cases the region of support is finite. Now, let us see that using these B-splines how we can go for interpolation. As we have said earlier that using these B-splines, a function is approximated as f t equal to p I b I 1 t or b I k t, where I varies from 0 to n. So, in this case let us take the value of k to be equal to 1, that means we have a B-spline of order 1, and we have shown that if we have a B-spline of order 1, then the nature of the B-spline function is it is constant between I and I plus 1, and which is equal to 1. So, using this, if I try to interpolate this particular function as shown in this diagram, which are nothing but some sample values, I take say t equal to 0 here, t equal to 1 here, t equal to 2 here, 3 here, 4 here, 5, 6, 7, 8 and so on. Now, if I want to find out say f of 1.3. So, f of 1.3 should lie somewhere here. So, to find out this f of 1.3, what I have to do is I have to evaluate this function f t, where I have to put t is equal to 1.3, and this f t is given by this expression, that is p I b I 1 t, where I varies from 0 to n. Now, find that this b I t, when if I take I equal to 1, so b 1 1 is a function like this. So, in between 1 and 2, this b 1 1 is constant and that is equal to 1. Okay. So, if I find out the value at this particular point, it will be p I, that is f s 1 multiplied by b 1 1 at t equal to 1.3, and which is equal to 1. And this B11 is equal to 1 for all values of t from t equal to 1 to t equal to 2, but excluding t equal to 2. So, if I interpolate this function using this bi1t, you will find that this interpolation will be of this form. Sorry. This interpolation will now be of this form. So, it goes like this. So, all the values at all points between t equal to 1 and t equal to 2, the interpolated value is equal to f s 1. Similarly, between t equal to 2 and t equal to 3, the interpolated values is equal to f s 2 and so on. Similarly, if I go for interpolation using say linear interpolation, where value of k is equal to 2, in that case again you find that if I put say t equal to 0 here, t equal to 1, t equal to 2, t equal to 3, 4, 5, 6, 7, 8 like this. Now, B12 is a linear function between 1 and 3. So, B12 is something like this. Similarly, B22 is something like this. B32 is something like this. So, if now I want to interpolate or I want to find out the value of this function at point say 2.5 at t equal to 2.5 say here, then you find that the sample values which take part in this interpolation are f 2 and f 3, and by using these two sample values by linear interpolation, I have to find out what is the interpolated value at t equal to 2.5. Now, you take a case that I want to interpolate this function value f t at t equal to say 3.1, that means somewhere here. So, if I want to do this, then what I have to do is this will be an interpolation of P 3. So, this will be nothing but P 3 into B 32 at point t equal to 3.1 plus, you can easily find out, it will be P 4 into B 42 again at point 3.1. So, I want to interpolate this value here. Now, find that weight of this P 3 is given by only this much, whereas weight of this will be P 2 B 22 and P 3 B 32. So, weight of B 2 is given by this value, whereas weight of P 3 is given by this value. So, when I am interpolating at 3.1, I am giving less weightage to P 3, which is nearer to this particular point t equal to 3.1, and I am giving more weightage to this particular point P 2, which is away from 3.1, which is not very logical. So, in this case, we have to go for some modification of this interpolation function. So, what is the modification that we can think of? The kind of modification that we can do in this case is, instead of having the interpolation as say f t, is equal to P I B I K T summation over I equal to 0 to n, I will just modify this expression as F t is equal to, I will put same B I P I, but B I will shift by some value. So, I will take it B I minus S K T, again I will vary from 0 to n, and the value of this I will be value of this shift S will depend upon what is the value of k. So, I will take S is equal to 0.5 if I have k equal to 1, that is constant interpolation. I will take S equal to 1 if I have k equal to 2, that is linear interpolation, and I will take S equal to 2 if k is equal to 4, that is I have cubic interpolation. Now, you find that I have not considered k equal to 3, which is the quadratic interpolation, because quadratic interpolation leads to asymmetry in interpolation. If I go for other interpolations like k equal to 1 with of course a shift of b I k by a value of 0.5, so s equal to 0.5, or if I take k equal to 2 with s equal to 1, or if I take k equal to 4 with s equal to 2, what I get is asymmetric interpolation. So, these are the different interpolation, the B-spline interpolation functions that we can use for interpolating the function from sample values. So, this shows the situation when we have shifted this b I 1 by a value 0.5. So, here you find now that b I 1 is constant from minus 0.5 to plus 0.5. Similarly, 0.5 to 1.5, it will be from 1.5 to 2.5 and so on. Similarly, b I 2, now it is the regions of support for b 0 2 is between minus 1 and 1, for b 1 2 is from 0 to 2 and so on. So, by using this, similarly for cubic interpolation, I do the corresponding shifting, and by using this, now the interpolation can be obtained by as, if I go for cubic interpolation, that f t is equal to p I b I minus 2 4 t, where the summation has to be taken from I equal to 0 to I equal to n. And here it gives that if I want to interpolate this function at this particular point, the weight given by this particular function sample is only this much, the weight given by this particular sample is this much, the weight given by this particular sample is this much, the weight given by this particular sample, this sample is weighted by this much. So, by taking this weighted average, the weights given by these B-spline functions, I can find out what will be the interpolated value at this particular location. So, if I use that cubic interpolation function, possibly I will have for this set of sample values an interpolation, a smooth interpolation like this. So, maybe this kind of smooth interpolation is possible using the cubic B-spline function. Now, let us see some of the results on the images that we have obtained. So, this is the example of a scaling operation. I have a small image which is scaled up by a factor 3 in both x direction and y direction. You find that the image on the left side is obtained by scaling without applying any interpolation. So, obviously, you find that here the image appears to be a set of dots where many of the pixels in the image are not filled up. If I go for nearest neighbor interpolation or constant interpolation, this is the reconstructed image that I can get, and you find that here I have the blocking artifacts. I mean, the image appears to be a collection of blocks. Similarly, if I go for other interpolation techniques, if I use quadratic B-spline interpolation, then this is the quality of the image that we obtain. If we go for cubic B-spline interpolation, then this is the quality of the image that we can obtain. The same result is also the same experiment is also done in case of rotation. This particular image has been rotated by 30 degrees, and if I do not apply any interpolation, so without interpolation the rotated image is shown on the left hand side, and here again you find that there are a number of black spots in this rotated image which cannot be filled up, which could not be filled up because no interpolation was used in this case. Whereas in the right hand side, this particular image after rotation has been interpolated using bicubic interpolation function. So, you find that all those black spots in the digital image have been filled up. Now, let us see the answers of the quiz questions that we had given in the last class. In the last class, we had given a quiz question for finding out the 3D coordinate point of a world point, where its coordinate in the left camera and the coordinates in the right camera are given. The value of the focal length lambda was given as 40 millimeter, and the x coordinate in one case was given as 0.2 in the left camera, and in the right camera it was given as 0.4, and the camera separation was given as 6 centimeter, that is 60 millimeter. So, if I simply use the formula, say z equal to lambda plus lambda b by x 2 minus x 1, you find that this will be equal to 40 plus 40 into 60 divided by 0.2, because x 2 minus x 1 in this case is 0.2, and which comes out to be 12040 so much millimeter. Okay. So, this is the value of z, that is the depth information, and once I have the value of z, then the 3D coordinates x and y can be computed from this value of z. So, x is nothing but x naught by lambda into lambda minus z, which is nothing but 0.2 upon 40 into minus 12000, which is equal to minus 60 millimeter, and by applying the same procedure you can find out y equal to minus 90 millimeter. So, this is about the first question. Second question was to find out what is the minimum depth that can be obtained by using the stereo camera, where the geometry of the stereo camera was specified. Now, this is also very simple. What you can do is, you find that we have two cameras with certain dimension of the imaging plate. They have been specified certain focal length, and if I just find out what is the limit of the image points. So, you find that if there is any point beyond this particular line, this point cannot be imaged by the left camera. If there is any point in this direction, that cannot be imaged by the right camera, because it goes beyond the imaging plate. And also, for finding out the depth information, it is necessary that the same point should be imaged by both the cameras. So, the points which can be imaged by both the cameras are only the points lying in this particular conical region. The points belonging to this region or the points belonging to this region cannot be imaged by both the cameras. So, all the points must be lying within this. So, the minimum depth which can be computed is this particular depth. Now, I know what is the separation between the cameras, I know what is the dimension of the imaging planes. Okay. I also know what is the focal length. So, from these informations, by using the concept of similar triangles, you can easily find out what is the minimum depth that can be computed by using this stereo setup. Thank you.